I'm here talking about a vulnerability we discovered called LeftoverLocals. And by the end of this talk, you'll understand very technically why we called it that. But what this does is this allows an attacker to listen to LLM responses through leaked GPU local memory. As a brief overview, call this vulnerability LeftoverLocals. We have this nice AI-generated logo for it, like all security vulnerabilities get these days. We discovered it last summer in 2023. We showed that it impacted GPUs from AMD, Apple, Qualcomm, and Imagination. We reported it or released it publicly after working behind the scenes with these companies. We reported it publicly January 16th. Made a little bit of a splash. It got reported by Wired magazine, and Forbes got some tweets from some kind of leaders in the AI community. What we're going to do in this talk is just overview the technical details of this vulnerability and kind of think a little bit deeper about the vulnerability of this, or the security of the systems that we run all of our cool AI stuff on. Nail down what this is. Two users co-resident on a machine with a GPU. One of them is the victim and one of them is the attacker. When we talk about users, we use this term very abstractly. This could be another application on your machine or just any other process that has this security boundary between it. And the victim is running an LLM using an open source model, for example, from Hugging Face. And of course, if you're using an LLM, you want to accelerate it on the GPU. What we show here is that the attacker can listen in and see the responses from the victim's LLM on GPUs from AMD, Apple, Qualcomm, and Imagination GPUs. And let's talk about how we actually do that. So to understand that, we need small ingredients kind of across the execution stack for ML workloads. We need to understand a little bit about the GPU architecture and execution model. We need to understand a little bit about how DNN operations are computed on GPUs and understand a little bit about LLM architectures and models. And all of the code that I show today or even discuss, it's all released open source. Here's the GitHub. So if you're curious about whether the GPU on your machine is impacted, you can always go try it out. And also happy to engage on that if anybody has any questions, either now or later if you try it out. Let's jump in. We as you saw, we have a lot to cover and not so much time. So let's talk a little bit about GPU architecture. And I'm not sure what the background of folks here is. I guess we have a wide variety of backgrounds. So I'm not really going to assume anything. But I'm also not going to try to cover all of GPU architecture in 1 hour. It's a huge topic and people write huge books. So we're going to just look at what we need. Let's think back to kind of what we know about architectures. And maybe some of us have more of a traditional architecture background where we think about CPUs. Well, if we zoom out far enough, GPUs aren't that much different. GPUs have cores, and I'm showing a little core here. And these cores access main memory. And so on discrete GPUs, this is VRAM. On integrated GPUs, for those of you who have a MacBook or in your smartphone, this just shares the same DRAM as the CPUs have. So, cores and memory, that seems pretty basic for architecture. What makes GPUs powerful is that they have lots of cores. For example, in the NVIDIA A100, it has almost 7,000 of them. This is where we start to get a bit different. I'm pretty sure your laptop doesn't have 7,000 CPU cores. But then how do you sort of manage this much parallelism? Well, what GPUs do, so what's different? They organize this massive number of cores into what are called streaming multiprocessors, sometimes called SMs. And each SM has they call it a software managed cache. And this software managed cache is only shared between the cores on an SM. This is sometimes called shared or local memory. So for example, the cores here, they can all share this little cache or piece of memory here. Cores here, they can all share this little piece of memory here. Cores over here cannot reach in to the local memory on other SMs. This is all kind of local to your streaming multiprocessor. And when I say it's a software managed cache, when we program CPUs, traditionally, we don't really think too much about the caches. We think, we access memory and then underneath the hood, it gets loaded to the cache or it gets invalidated. On the GPU, you have to load it yourself. You have to say, take this piece of memory from main memory, put it in local memory, and then I'm going to access it from local memory. It's up to you as a programmer to do it. Probably one of the reasons why GPU programming is oftentimes not considered as simple as CPU programming. So let's talk a little bit more about local memory. If maybe you could tell, but from like the title of the talk, this is kind of where we're going to be looking. So local memory, some properties of it. It's not specified to be persistent. So whatever you compute here, if you want to save it if you're doing like an AI inference, and if you want to have that result and ship that result back to the CPU, you're in charge of flushing anything out here that you want to save from local memory to global memory. It's also limited in size. I mean, I know GPUs always are limited in memory, but these local memory regions are only about 65 kilobytes per SM on many GPUs. Occasionally, some GPUs are a bit bigger or smaller, but that's a good rule of thumb. But the thing about them is they're very fast. So for those of you who know more about GPUs, you know that memory is very long latency. It's high bandwidth, but long latency. And you don't want to access main memory very often. And because of this, whenever, again, for those of you who have taken a GPU programming 101 class or anything like that, typically using this local memory or shared memory is one of the first things you learn. Is basically any memory that you're going to use, load it in from your slow global memory and put it in your local memory. This was a very simple overview. There's much, much, much more. And if this is an image from NVIDIA's white paper. This is from the Kepler architecture. It's it's a bit old now, but it's one of my favorite architectures. But what you're going to see is that there's lots of different memory regions. There's texture memory down here, which is mostly used for graphics. There's read-only memory right here. There's huge register files. There's shared instruction caches. So we had a very simplified view, and throughout this talk, I want you to think, if we're just simplified our view so much with this vulnerability, I want you to think about what other vulnerabilities could be lurking in here as well. So we kind of saw how the GPU is set up, but how the heck do you program these things? So we need to talk a little bit about the GPU programming model. This is kind of a fractured community. On one hand, you have CUDA, because CUDA is the programming language for NVIDIA GPUs. It tends to be quite popular right now. You also have things like Kronos, where they have OpenCL, and Vulkan, which are a little bit more cross-platform, even if they're not widely deployed. Apple has Metal, so on and so forth. But what we're going to do is we're going to try to translate between some of these, because some of you might be familiar with one framework and maybe not another. So CUDA, the base unit of computation, is called a thread. Again, if you've done multi-programming in CPUs, your intuition will hold here. A thread is executed on a core. In Kronos, they call these things work items or invocations. Then what you can do is you can cluster threads in the programming model into what's called a thread block. And the threads that are clustered into a thread block are all executed on the same SM. In the Kronos terminology, that's called a work group. And then kind of all of your threads that execute an entire GPU programming or an entire GPU program, which is called the kernel, is called a grid in CUDA or an ND range in Kronos. I really don't like that terminology, but yeah, and that's executed across all of the SMs on the GPU. Knowing that, what does a GPU actually execute? Well, a GPU, typically when you program them, a GPU executes what's called a GPU kernel. Kernel is another one of these words that is completely overloaded in computer science. But in this talk, a kernel is going to be an entry point for a GPU execution. An application typically executes many GPU kernels, and each kernel typically does not execute for a very long time. And a lot of us are probably familiar with AI and ML workloads. For example, one layer in your DNN is going to be a GPU kernel, because one layer is going to be a matrix multiplication or a convolution. And so, that gets executed as a kernel, and then the GPU program stops, and then you execute another one, and you execute another one. And that's typically the model that a GPU kernel has. The CPU essentially stages all of these kernels. So the CPU code, sometimes it's called the host, copies memory to GPU, and it launches the GPU kernel. It basically preps the memory and says, okay, now you go GPU. Preps the memory, says you go. It specifies how many threads, and it specifies the size of the work groups, and so on and so forth. So if we look at a little bit of code, we're not going to look at a ton of code today, but if we wanted to add together a vector in OpenCL, you have a kernel function. You sort of specify it with the special word kernel, and then you have some pointers to GPU memory. This says it's to the global or the main memory in the GPU, A, B, and C. What you can do is you can grab your thread ID using built-in APIs. So you'd say get global ID, and then essentially every thread does one of those additions. So the kernel itself is quite simple. And then on the CPU staging part, what you do is the CPU typically allocates memory on the CPU using malloc, initializes that memory. This is just from an example online. And then what it has to do is it has to malloc the memory on the GPU using special GPU APIs. This is saying create a buffer on the GPU, create a buffer, and then it copies the memory from the host, from the classic CPU memory to the GPU. And then finally, when the memory is all staged, it enqueues that kernel, which basically tells the GPU, okay, your memory's ready. Now you go do this. And so this is sort of the interplay of what the CPU does, what the GPU does. GPUs tend to do kind of smaller, simpler, data-intensive computations, where the CPU preps the memory and everything like that. So now if we think about how this GPU kernel gets mapped to the GPU hardware. So for example, if we have a GPU with one SM, you compile this, it gets put on the GPU. For example, if we had a size of 4096, typically a work group size is something around 256. That means we'd need 16 work groups to execute all to make sure we had one thread per item in the vector. And what's going to happen is our GPUs are typically too small to handle as many threads as we need. So what happens is that the first work group is going to get put on the SM, and then it's going to execute till it's done. Then the second work group is going to get put on, then the third work group, then the fourth work group. And it's going to give you as a programmer the illusion that you have as many threads as you need, even if they execute kind of sequentially over here. So now we know a little bit about how programs execute on the GPU. Let's talk about how we have GPU multiprocessing. So you see this all the time on your laptop. In fact, I guarantee multiprocessing on your GPU is happening right now. You're going to have graphics executing at, various applications are going to be calling different graphics kernels. Potentially, if you're running AI in the background, that's going to be running on your GPU, so on and so forth. So different processes can share the GPU. So if we have an example, a GPU with two streaming multiprocessors, and if we have two processes sharing the GPU, so process 0 executes, these kernels, process 1 executes these kernels, and I'm going to color code this so it's a bit easier to see. One very natural thing that you might think is, say, we have two processes, we have two streaming multiprocessors. Maybe, process 0 can just own the first streaming multiprocessor. Process 1 can own the next one. This is how it works for CPUs. And if you launch a multi-threaded application, and if you have the threads, one of your threads, will own one of your processors, and so on and so forth. And things can move around a little bit, but typically this is the general model for CPUs. GPUs don't do this, however. There are some virtualized environments, and we'll talk about them at the end of the talk, but typically GPUs look like this. One kernel will own the GPU the entire time, and then the next kernel will own the entire GPU. And the reason why this works well for GPUs is, like we said, kernels typically don't run for very long. So it's not like the red kernel will have to wait for too long. These kernels are typically quite quick. If we think about vulnerabilities, even with this model that we had over here, we can probably think about some bad things that could happen. One bad thing that can happen is, for example, if this blue kernel, what if it decides to have an infinite loop? We've all written infinite loops in our program. And this actually came out of my previous research group. What happens though is GPUs are special because if you lock up the GPU, what happens is, you're no longer going to be able to interact with your operating system, because GPUs, as their name implies, are also in charge of graphics. And so, like I said, this was part of my previous research group. And what they did is they went to a website and they put an infinite loop on the GPU from a website. And what happens is they can actually, let's see, give it a second. And there it goes. If they don't terminate correctly, you can put the system in a very strange space. And on some interactive systems, like, maybe on your operating system or on Windows, you can actually, crash the entire system. And so this got a CVE back in 2017. GPU vendors have worked on this a little bit since then. Things are a bit better, but I think there are still issues. Let's think about a different type of vulnerability. Let's think about a memory leak. So if these are two kernels, and if they're from different processes, can this kernel, the red one, ever read data from the blue one? Can it ever read, data from a previous process? And, maybe you wouldn't be surprised to learn that the answer in the past has been yes, and researchers have shown this. So this was a paper from 2014. Essentially what they did is they just launched a kernel and it just dumped a bunch of the texture memory. And what happens is you can then get a histogram of the colors that you see, and you can, kind of infer, what the previous user was looking at. So yeah, this has happened in the past. There's also a more recent vulnerability that's pretty interesting called GPU zip. Again, it's a little bit more of a side channel type approach, but it's essentially a way for one kernel to get information from another. This one leaks pixel data. It's pretty interesting to look at. I highly suggest checking that out if you're interested in this. But the thing is they probably shouldn't, because classically, the classic security model on our systems are process isolation. One process should not be able to communicate with another process, except, if they're going through a network or some, approved channel. But, you just shouldn't be able to read each other's memory. And in fact, it's very hard to find GPU specifications about this. Luckily, Khronos does say something. Khronos says that any guarantees made by an operating system about whether memory from one process can be visible to another process must not be violated by a Vulkan implementation for any memory allocation. But, this is one sentence in a massive specification. And, I think we need to do a little bit more work here, but it seems pretty clear that processes should not be allowed to read each other's memory. What we look at here is, can process 1 read leftover local memory from process 0? And you can kind of test for this. The way that you can write a simple test is if process 0 writes, a canary value. So just pick your favorite number and just have process 0 write that over and over again to its local memory, and then have process 1 just go and dump uninitialized local memory and try to see what you can see. Again, just because, GPUs kind of have a rich history and a lot of people kind of got in early and poked around, this has been kind of shown before. There's this paper back in 2013. I think it's a great paper. And what they did is they tried to look at the GPU architecture and try to explore all the different places that memory can leak. So they've done similar experiments in the past. What they did back then is they just focused on CUDA. So when you ask if NVIDIA is immune, back in 2013 they weren't, because this paper showed that NVIDIA GPUs leaked memory all over the place. Maybe NVIDIA saw this paper and at that point, maybe that's why we don't see as much leaking on NVIDIA GPUs now. But they kind of just laid the foundations. They kind of said, yeah, this can happen and people should be aware. Highly suggest this paper. What we wanted to do is kind of revisit these ideas, both in the modern age, because we have a lot more GPUs now, and in the modern age of applications. This is back in 2013. I don't even know that people were really running DNNs on GPUs back then. So what we did is we designed an OpenCL command line tester, a Vulkan command line tester, an Android app, an Apple app that works on iPhones and iPads and on your machine. And we just, tried to test every GPU that we could get our hands on. Just to give you a quick visual of what this looks like. Let's see, I'm actually going to exit here so that I can control this a little bit better. So we have two processes. We have the yellow one and the red one. The yellow one's going to write. And the GPU can only execute one kernel at a time. So what's going to happen is the writer process is going to launch its kernel. It's going to get on the GPU. The writer is going to write some canary values. Let's say 1, 2, 3. Let's say that's your favorite number. So it's going to basically have all of its threads write 1, 2, 3 to local memory. Now, the writer is going to finish, but what our hypothesis is, what we want to check is if those canary values remain, then the listener can get on the GPU, and then it can dump that uninitialized local memory to global memory. Then once that kernel finishes, the listener can copy that memory back and get values from the writer process. So overall, I don't know that that's super complicated, but that's a visualization of what we have. I do have a demo of this running on my MacBook. What I want to do though is I want to make sure that we get through all the material. So maybe I'll save the demo for the end and we can see. We did this and then we just ran and we tried to see if we could see those canary values. We were a little bit surprised just how many GPUs we saw this on. So we saw it on my iPhone 12. I've since updated and I didn't see it on my new iPhone, but iPhone 12 showed it. I had an older iPad that showed it. My M2 shows it, a bunch of AMD GPUs show it, and a bunch of Qualcomm GPUs show it. So, the Qualcomm GPUs, they're what's going to be on sort of your kind of high-end Android phones. So yeah, we kind of saw this all over the place, and we were a little bit surprised. We went and we tried it on other devices. For example, we tried it on like the Google Pixels. I know those are popular smartphones. Interestingly, what we saw on the Pixel is we never saw the canary values. Like we never saw the exact values that we were writing from the writer, but we did see non-zero values. And as a security-minded person, every time you see a non-zero value, red flags there. But we reported this to ARM, and ARM sort of confirmed that these non-zero values weren't actually coming from across the processes. So that was good. We did not observe violations on NVIDIA GPUs, Intel GPUs, and in our initial testing, we didn't observe them on Imagination GPUs. Some of you might not know Imagination. They're a company, they used to make the GPUs for Apple devices. They're a company that's based in the UK. These days, they make GPUs for some of the other Android devices. It seems to be that they end up being more in sort of some of the budget devices, like this is in the Motorola MG phone, but they still have a lot of GPUs out there, so we shouldn't count them out. And later after we released this, the Imagination people actually came back to us and said, "Hey, we're actually impacted," but they had a patch, and so we worked with them on that. Basically, what we showed is GPUs are kind of leaking data through this local memory, and a bunch of GPUs are doing it. So what's the big deal? Like, what sort of applications can this impact? And the truth is it probably impacts a lot of applications. Like, when you learn how to program GPUs, using this optimized memory region is kind of one of the first things you learn. But because LLMs are exciting, that's what we sort of looked at. We tried to think about how this could impact LLMs. So what we did is we looked at llama.cpp. It's a really cool open source LLM. I love it because the code is not super complicated. You can really dive in and you can really see the guts of some of these GPU programs that are actually running on it. What's also really nice about it is that it supports GPUs from a lot of different vendors. Of course, it has CUDA for NVIDIA, but it also has Metal for Apple, and it has OpenCL that can target a lot of others. So, because of this and because, our testing was it aimed to be cross-platform, we thought this was a good code base to look at. The other thing to note about kind of how LLMs work is, there's sort of a DNN as their foundation. And the example that we used has about 33 hidden layers. The way to visualize, as we've all seen, a DNN is that you have your input layer, and then they go through these various hidden layers, and finally you get to your output layer. And in this case, each layer is a matrix multiplication. So, you can imagine doing a matrix multiplication with the weights here, matrix multiplication with the weights here, and so on and so forth. And of course, these matrix multiplications are accelerated by the GPU. Each of these matrix multiplications is going to be one of those kernels. Let's think about how matrix multiplication is actually accelerated on a GPU. In our earlier example of the vector addition, we didn't use local memory at all. We just said, hey, every thread, go grab a memory and add it together. Matrix multiplication is a bit more complicated, and because of that, you actually do want to use local memory. So this is a great figure from this webpage that I borrowed. For those of you who have worked on done programming or any sort of optimization programming, this is one of the first optimizations you learn. It actually works on the CPU as well. But if you want to multiply some big matrices together, like A times B, what you can do is you can actually decompose it into smaller problems. If you want to compute this purple region of C, your output, you can actually say C equals, this light green times light blue plus dark green times dark blue, these two. And you've basically decomposed this big problem into a smaller problem. And guess what? You can cache these smaller matrices in that local memory that actually makes them very fast to do these sub-problems. And any optimized matrix multiplication on a GPU is going to be caching these sub-problems in local memory. I see that I have Leaky Llamas as the name. That was its working title, so I haven't quite done the search and replace throughout all the slides. But yeah, so this basically shows that when you are doing these matrix multiplications, you are using the local memory quite a bit. And now if you kind of set up the attacker is actually pretty simple. The victim is running the LLM, and essentially the kernels it's going to be doing is one of the llama layers, 0, 1, 2, 3. Those are all unique GPU kernels. And then all what the attacker really has to do is they just do a memory dump. They say, launch my kernel, and I'm just going to dump whatever's there. And you're not guaranteed to get exactly a stripe. This is up to the operating system, up to complex drivers. But really, you can try to go for this, and it turns out that on a modern system, you can get interleavings like this. So basically, llama.cpp executes a layer, you go dump, and you can get a bunch of the values from it. The next layer, the next layer, the next layer. We can basically steal about 3 megabytes of weights per layer, and we can steal about 3 megabytes of intermediate computation. It's 3 megabytes is nothing to sneeze at, but at the same time, these are giant models. These models are gigs large, in the tens of gigs. But what you can do is, if you are stealing enough weights, you can kind of look at them and you can say, do these weights match up any patterns of maybe open source models? So essentially, we say that you can use these weights to fingerprint it. So if process 0 is using an open source model, for example, from Hugging Face, you can essentially grab those weights and you can go figure out which model they're using. And that's going to play a part in the final attack. When we actually complete this attack, one layer is more interesting than the others. And you might be able to guess which layer that is. It's the output layer. And if the attacker can get the inputs to this matrix multiplication, then we can get the output. So for the model I'm using, it was one of these ones from Hugging Face. I think it was a 7 billion parameter one. The weights at the output layer have this dimension, a 32K by 4K. But the input is, just 4K. The weights are too big to steal. We're not going to be able to steal the weights. But like I said, we can fingerprint it. We have so much data that if the user is using an open source model, we can look for patterns throughout the layers, and we can essentially get the model from Hugging Face. Now, the input actually ends up being quite small. That's just 4K. We said, local memory, the region that we're stealing is about, 65K. So this local memory actually fits into, or this input fits into local memory. And so what we can do is we can use the weights that we fingerprinted earlier, and we can then steal this, and the attacker can just do this computation itself and get the output. And that's sort of how this attack all comes together. There are a few assumptions here. For interactive mode, the output layer is a matrix vector multiplication. GTML is sort of the linear algebra library that llama.cpp uses. It kind of has a strange matrix vector implementation. It doesn't really cache the input in a straightforward way. So what they do if you were to grab llama.cpp off the shelf, the way that it does matrix multiplication is it takes a row of weights, it does the input, this is what we want to steal, and essentially it creates partial sums, and those partial sums are stored in the local memory. So we can steal these partial sums, but we can't really steal that input as straightforwardly as we would like. Now, when we were investigating this, what we said is, there are techniques that you could use, probably like linear constraint programming. I'm not an expert in that, but essentially you have this situation where the weights because you have them fingerprinted. You want to know the input, but you have the partial sums. You can sort of set up this linear equation. Like I said, it would probably require inverting a large matrix, so it might be kind of difficult, but you could still probably get it. And it would be cool if somebody wanted to look into this. But at the end of the day, time is finite, and I'm basically working 2 jobs sometimes. So I said, let's actually go with a more performant matrix vector implementation. And in that way, what you do is each thread is basically assigned a row in the weights, and then the input vector just fits in local memory, and all of the threads share the input vector that's in local memory. It's very optimized. This is very idiomatic. And this is kind of the matrix vector multiplication that we plugged in that was a little bit easier to steal. Like I said, the other way, it's possible. And, typically hackers tend to have a lot of time. So I wouldn't put it past a malicious person to spend that time. But for our prototype, we did this optimization here. Let's talk a little bit about the impact of leak that there's already been some questions on. So are you safe? In the high-end systems, AMD and NVIDIA physically partition the GPUs for virtualization. This isn't widely deployed yet, but this is like vGPU for NVIDIA. AMD calls it MX GPU or something like that. And what they do is they will give you this more kind of traditional multiprocessing where one process owns one SM and another one owns another SM. And at that point, they don't have access to each other's local memory. So for those high-end virtualizations, this problem goes away. The other thing is that AWS and Azure, they don't allow multi-tenant access to their GPUs, which means if you go and if you rent a machine from AWS with a GPU on it, nobody else is going to be on that machine. I think, it would be nice if they would share the GPU, but I imagine they're kind of aware of security issues like this and many others so that they don't really allow multi-tenant access to their GPUs. I think it'd be cool and if we could figure this out, because I think it might make GPUs a little bit cheaper if you could share them. But we have to solve this first. There's things like Web GPU, which that executes GPU kernels in the browser. I don't know. For those of you who haven't seen that, it's very cool. Basically, it allows you to run like DNNs on your local GPU in the browser. Again, the teams that, for example, at Chrome who are working on this understand some of these security issues. And what they've done is they've added compiler passes that essentially will not let you access uninitialized memory. So they're kind of doing their job there. But there's a lot of other use cases. Like, for example, if you just launch an application on your local machine, like I know there's a lot of local LLMs out there, there's not really going to be protections there. So, you really need to be careful. And, there's a lot of creative people. And I'm not saying this to dunk on anyone. In fact, I think this stuff is great. This is just a tweet I got forwarded the other day. This person built a distributed training module from scratch that works on Apple GPUs. That's awesome. I want people to be able to do this. But, you have to be careful because Apple is one of the GPUs that we saw just leaks all this data everywhere. And unfortunately, I think that a lot of people aren't thinking about security very much when they do stuff like this, which either we need to get our systems more secure so that people don't have to think about security, or we need to kind of bring security concerns into people's minds. The current state. So Qualcomm and Imagination have issued a patch, so those GPUs tend to be okay right now. Apple has said they patched some devices. The M2 that I have on my laptop is still impacted. My phone was not impacted though, so apparently that patch went through. So, Apple hasn't really said too much more than that, so we'll have to see if they continue to patch their systems. AMD promised a patch. We're not sure if it's out yet. They haven't talked to us. So I need to go investigate that a bit further. When you're dealing with so many different GPUs, it's hard to kind of keep them all up to date and run your regression tests on them. But, they did take this seriously and they are working on it. There was a question in the chat about whether there's a CVE for each vendor. The way we did this is we worked with CERT, which is one of these organizations that coordinates these disclosures. And we discussed whether there should be a CVE for each vendor. And in the end, we decided just to have one CVE that covers all of them. I can do a really simple demo. This is essentially the GIF that we saw. So what I can do is I can run, this is a local LLM. For those of you that were interested in the model, it's this, I don't know the different models very well, but this one is Wizard LM 7 billion. I picked it because it was big enough, or it was small enough to run on this AMD GPU, but big enough to still be interesting. So what I can do is in this process, I can start running. It loads up to LLM and it sort of seeds it with a little prompt here. What you can do is you can, basically have this prompt. But what I'm going to do over here in this other process is I'm going to run this, what I call the covert listener. And it's just going to sit over here and it's modeling an attacker. Now, what you can probably see is like, I'm the same user. That isn't necessary. We've shown that this works across Docker containers. I'm only the same user because it makes the demo a little bit easier. But we could say something like, tell me about San Jose. And the user could just be using an LLM like we all do. And so we get a response about San Jose being a city in California, in Silicon Valley. And then over here, the listener, it's always fun to kind of see the different things it says. And occasionally the weights it's not the weights. Occasionally the input can get a little mixed up and you get a little bit of garbage. But yeah, it actually, you can see like in real time, we're able to get pretty good response. Like California, we're getting this weird like couple of seals, but it's not perfect because essentially we're relying on the GPU to kind of schedule us immediately after that output layer. And you can see in a lot of cases we get it. You could start to fine tune this attacker. Like we didn't do much work on like trying to set up the timing and stuff. It just happens to work pretty well as it is. So this is the Apple application I have, and it's going to be running on my M2. And this kind of can, like what this does is this isn't going to do the AI proof of concept. This is just going to check for leaking memory. This is going to be one of our more basic probes. This is a kernel. This is written in metal. So all of this is going to look a little bit different, but they should all kind of smell kind of the same. So I have this listener kernel. And what I do is I create this local memory. So this is kind of how you have to do this in the GPU programming languages. You create a set of local memory. I have it to be, 8K big. And then what I'm essentially going to do is I'm just going to iterate through this local memory. And, I haven't initialized it, so I'm going to iterate through it. I'm just going to dump this to global memory where I can examine it later on the CPU. So what I can do is I can run this. The first thing I'm going to do is I'm just going to search. This is just going to give me a dump of uninitialized local memory. It's going to give me a histogram. So if I search, what this says is it says, I saw the value 0 this many times. So it's kind of a histogram. So we're only seeing zeros. So you might think, the memory's gotten cleared. Like usually when you clear memory, it's 0. So this looks okay. So where's the security issue here? For technical folks, especially people, if you have a compiler background, what's actually happening here is that the compiler is seeing that we're accessing uninitialized memory. And a compiler is smart enough to say, hey, if this is uninitialized, it can be anything. So I'm going to give it zeros. So what you have to do is you have to kind of trick the compiler. What I have is this commented out code here. And I'm tricking this. When you trick a compiler, especially for GPUs, it's more art than science. But what I'm saying here is if I can have just a couple of threads, this is just going to have just 2 threads with ID less than 2. I'm going to have it go in and I'm just going to have it write something to local memory. So I'm just going to take 2 spaces out of our 8K and I'm going to write something here. In fact, I think this could probably be 1. But now the compiler has a difficult choice. The compiler says, hey, somebody's writing here and somebody's reading. So at this point, I can't prove that that's completely uninitialized. And so I actually have to go to memory and I actually have to do this dump. So now when I search, you can see I get a bunch of garbage. So this is stuff that's left in local memory, probably from the graphics that's running. I think sharing my screen on Zoom is probably running some graphics. So some of this, even though it's a simple idea, some of it you have to scratch your head and say, there's protection layers here, and I need to think about clever ways how to get around them. Turns out though, if you know a little bit about compilers and how the code is executed, you can get around them. So now I have another process on my M2. And what I can do is I'm going to seed this. So right here, you need to give it an anchor. This is how covert channels work. So I'm just going to give it XYZ. This is some pattern that the listener can listen for. And I can say, hello, BuzzRobot. And then what the writer can do is the writer's going to say, I'm going to write this secret message along with this anchor. I'm going to write that to local memory. Now, if we go back to our listener, and if we search again, we're not seeing zeros. We're seeing values, but we're seeing a lot less of them. And if we say, maybe this program, this would happen in like a Trojan. Maybe they've agreed on a secret key of XYZ. And so if they agree on a secret key, and if we look for that, then we can say, we can find that message between applications. So they agree on the anchor, and then anything that I write over here, this is a secret message. I'm going to start writing that one. Oops, go to the listener. And so this essentially allows this is kind of how viruses work, right? Like if you have a Trojan in your application, they sort of agree on an anchor. And then now at this point, I'm communicating through 2 processes that should not be able to communicate this way. And it's only like after you do this, then you can expand the vulnerability to do stuff in AI. But it's always kind of fun to do these little what these are called covert channels. And yeah, I mean, you can on your Mac, if you have an M2 like I do, this is still there. And while there's applications in AI, there's also this just opens up the door for like Trojans as well.